All right, thanks. Well, thanks everyone for being here, and thanks to the organizers for putting this together. My name is Meg Fowler, and today I'm going to talk about a project I've been working on for a few months, looking at the predictability of soil moisture in Northern California with my postdoc advisor, Dr. Cecile Penland. So before I dive into the science, I want to talk a little bit about why we want to forecast soil moisture at all. This isn't something that gets a ton of attention, but soil moisture plays a key role in a number of processes we really care about. It plays a role in feeding back to precipitation and precipitation recycling, especially for places that have really strong land-atmosphere coupling. It's also been shown to increase stream flow and flooding because if you have higher soil moisture and you have a rain event, that precipitation can't infiltrate the soil as well, runs off to nearby rivers and streams, and potentially increases flooding. It also plays a role in how we define drought and drought severity. A meteorological drought is one thing, but when plants can't access soil moisture, they really start to decrease in their productivity and potentially die off. Understanding soil moisture is especially critical for California. The state is vulnerable to a range of different extremes, and that's been particularly well illustrated in recent memory. We went through the multi-year drought from 2012 through 2015, which is one of the most intense droughts California has seen in the last few centuries. That was then followed by a historic water year that led to the Oroville Dam crisis in 2017. So understanding and predicting soil moisture can hopefully help us understand and predict these kinds of extremes. The other benefit of looking at California and Northern California in particular is that there's a pretty good network of observations of in-ground soil moisture and soil temperature. For our study, we're looking at 11 stations highlighted here in red on the right. 6 are taken from the NOAA hydrometeorological testbed, mostly located in the Russian River, and 5 are taken from the U.S. Climate Reference Network. Observing soil moisture is one thing, but predicting it is really hard. There are so many things that go into controlling soil moisture, from atmospheric inputs like precipitation and temperature, to land surface characteristics like is it urban and paved, or is there vegetation? If there are plants, what kind of root structure do they have? How thick are their leaves? How much area do they cover? And then we also need to know physical characteristics of the soil itself. Its texture and porosity really determine how well it holds moisture over time. That makes modeling this kind of difficult, but one really well-validated approach was first proposed in 1994 by Anticavi and Rodriguez-Iturbey. Essentially, this equation models soil moisture as it changes in time, as it relies on soil porosity, depth of the active layer, a loss coefficient, a diffusion term, and a driving noise which represents rainfall stochastically. Now, it's well-validated, it's very thorough, and it performs well at a single point. The issue comes in that you need to know each of these variables for each point you want to look at. So if we want to look at 11 different stations in California, or say we want to look at, say, 50 maybe across the continental US, you would need to know these characteristics of the soil at each individual location. There's no guarantee we have the observations to do that, or that they're at a good enough spatial resolution to warrant this. I'll propose today kind of an alternative. It's really similar mathematically, but it's purely data-driven. And by that, I mean you only need to know the conditions of the soil itself. So if we want to forecast soil moisture into the future, all we need to know is the historical soil moisture record at that site. The approach is called linear inverse modeling, or LIM. It was first proposed in 1989 by Cecile Penland, and it's been widely used since in a number of different studies, mostly focused in the fields of atmospheric and oceanic sciences. Most notably, it's used to forecast El Niño conditions in the tropical Pacific. It has skill that can actually rival that of fully coupled global climate models for predicting that. Overall, at a high level, the goal of LIM is to extract the dynamical equation that governs a system from its observed statistics. So rather than estimating each parameter individually, can we look at the statistics of the system and derive that equation? We do this by separating our system, X, into 2 components based on their timescale of evolution. So here, our change in X over time is given by a linear component, Lx, which represents the slower evolving, more predictable parts of growth, and then a stochastic term, which represents those faster evolving, harder to predict things like precipitation. Now, this equation is really similar to the 1994 equation I showed earlier. Essentially, this equation has 2 linear terms, which we can think of as kind of being combined into R's. And again, we're driving it with some stochastic noise, precipitation, for example. They're similar, but we're going to use a slight variation in that we will use a multivariate case. So instead of using S, which is just soil moisture, we'll use X, which is also including soil temperature to increase predictability. The soil temperature and soil moisture vary really tightly together. They co-vary very strongly. To get around that, we'll actually use residual soil temperature to include only the unique information that temperature adds to our system. Essentially, we take a linear regression between moisture and temperature, and we remove the part of soil temperature variability that's already accounted for in the soil moisture record. That way, we're not double counting variability. We'll also remove the average annual cycle from each station individually so that we're looking at soil moisture or soil temperature anomalies, because that's what really drives interesting things like floods and droughts. We'll also look at the z-scores of those anomalies, which we compute from daily anomalies at 10 centimeters over about a 5.5-year period from May of 2012 through 2017. Z-scores are really important here because soil temperature and soil moisture tend to vary on really different scales. If we want them to contribute equally to our equation, we normalize them in this way. So essentially, our system X can be thought of as a 2050-ish day record of residual soil temperature anomalies at 11 stations and soil moisture anomalies at 11 stations. We can then use contemporaneous and lagged multivariate statistics of our X to estimate those linear equations of motion. So we're using just the observed soil conditions to estimate the equations that control those in time. If we pair the initial conditions over 2050 days with those equations, we can make forecasts of how soil moisture evolves into the future. So one of the ways to look at that forecast scale is by looking at mean squared error, which is what I'm plotting here. Each station has its own error growth in time over 14 days, and we're looking at soil moisture errors in particular. One of the nice things that comes out of using LIM is that you get an estimate of the expected error of your forecast in advance, and we'll consider that skillful if the mean squared error is less than about 0.4. Now the benefit is that before we make any forecast, or in our case a hindcast because we're using historical data, you have some idea of how your error should grow. If we compare that to how the error does actually grow once we make these hindcasts, what's reassuring is that the green and the gold lines are really close together. So the model's working about as expected. The error is growing as we thought it would in advance. We can then compare this error growth to an AR1 process. Essentially, this is a persistent style forecast. The AR1 process will make its hindcast based only on the previous day's conditions of residual soil temperature and soil moisture anomalies. And at every station, the blue line falls above the gold and green lines, which means error is growing faster in the AR1 process than it is in our hindcast. So our model is outperforming persistence. There are a lot of variabilities depending on which station you look at. So Santa Barbara, for example, might maintain skill in our model for about 14 days. Healdsburg, maybe not, more like 5 or 6, maybe 7 days. But despite all of this, the main takeaway from this is that the AR1 process can't outperform our model. But we can improve our performance further. Not all forecasts are really created equal. Some have more skill than others, and that's something you're probably familiar with just by dealing with your own local weather forecast and how much it changes 5 days out to the time it verifies. The goal is identifying those in advance. Can we say with any confidence when we make a forecast that it is a good forecast? LIM gives us kind of a unique way to do this. We can use an optimization procedure applied to those empirically derived equations to identify what we will call forecasts of opportunity for soil moisture. The idea is that one of the things that LIM provides us with is a set of initial conditions that lead to the most growth in the system. We call this the optimal structure, which is plotted here in blue. Now, the key here isn't really the sign, but the magnitude. So if we have a strong positive contribution here at Rio Neto, strong negative value here at Bodega Bay, both are large values. Sign doesn't matter, but they're contributing to giving us a good forecast for moisture as a whole. These are the initial conditions in temperature and moisture that would lead to a lot of growth in moisture. If we look at what these conditions would look like, say 16 days in advance, we would have the red line. And you'll notice that the soil moisture anomalies in particular have grown quite a bit after this passage of time. If our initial conditions taken over those 2050 days are similar to our blue line, our optimal structure, we'll consider it predictable, more predictable than otherwise, and we should see a pattern of growth that's really similar to this red line, which is what the model is expecting. So what we can do then is look at the projection of our initial conditions onto that optimal structure And if it's a good projection, if it's strong, say in the upper tercile, that means they're very similar, and we expect these to be good forecasts. We can kind of test this hypothesis by looking at the mean squared error again. So here's the forecast mean squared error at each station individually out to 2 weeks. The gold line is just what you saw before. So this is our forecast error made on all 2050 days. And if we compare that to forecasts made only on that top tercile of initial conditions, or forecast of opportunity, our skill increases pretty dramatically. Again, it varies by site, but our maroon line is consistently maintaining skill longer than the gold line. Skill is maintained anywhere from 9 to 20 days, depending on which station you're looking at. And again, we can compare that to an AR1 process. Right now, the AR1 process is computed not over all days as it was before, but again, just on those days that fall in the upper tercile or forecast of opportunity days. And again, LIM is outperforming that. So we are outperforming a persistent style forecast. And that's one of the biggest things to take away from this. So this is really just a high-level recap of this new methodology, but LIM kind of offers us a new modeling framework for forecasting soil moisture anomalies in particular. When we built this model, at least for Northern California, it can maintain skill for anywhere from about 1 to 2 weeks, and that's in line with what some previous studies have found. But I think the most important thing that this approach offers is that LIM allows us to identify forecasts of opportunity. These days where we expect a forecast to be good. It extends our predictability further, and it helps give an estimate of the confidence in the forecast, which is critical not just for forecasters, but for end users too, to make decisions on when to act and how seriously to take these forecasts. So with that, I'd like to thank you for your time. My email's up here if you want to shoot me an email for more information, or I'm happy to take any questions. Thanks.